All right, here goes again. Okay, let me find this. Code development.
And maybe instead of parallel map, let's just try one.
Yeah, hold on. I don't know whether. I mean, I'm not sure this gray code thing is going to work at all, but I think we should try something which we really think is non-trivial, because by the time we get to 2.2, things should actually we should try the other. You know, things up here for 2.2s.
Mm-hmm. Yes, I agree. A total doesn't work too badly for spotting a pattern, and enough randomness will overwhelm total.
I'll believe it when I see it. I don't remember how many of these there are.
25 doesn't look too bad. Oh, that's the
No,
number
no,
of
no.
kernels. 37.
No, that's the number of kernels.
Oh, I see.
Let's just hope that the orphaned kernels died off correctly when the thing had to be restarted.
Right, right.
That's horrifying.
Have you seen the movie Into the Spider-Verse yet?
I have not seen Into the Spider-Verse.
There's one scene where Spider-Man needs to find a file on a computer, but the computer screen is a, a
Oh, maybe I
vastly
have seen it. When did it come out, actually?
2 years ago.
Oh, I probably have seen it. Yeah, I just wouldn't have known it. It's a Spider-Man movie, whatever.
Animated, but just
Oh,
a
no, I didn't
cluttered
see that.
mess.
Okay, look at this. There's no puppies of interest here.
Yes. Some look more random than others.
Take your pick. I don't think any of these look terribly interesting.
Yeah, I agree.
Now, the corresponding multi-way graphs maybe look a little bit more interesting, but I think, okay, let me just go back here. And I think the next case is the 32 choose. The next case up will be 32 choose 3.
Okay.
To choose 4, rather, which I think is very big.
Okay.
Well, that means it's too big for us to look at.
Oh, that's
35
too bad.
What's that? That's not
That's
that bad.
right.
Okay, let's make this. And it'll be slightly less than that because of the um, because of the non-determinism thing here.
Right.
I mean, the other case we can look at is where it's a pure deterministic thing where we just add one piece of non-determinism, but I actually think it's better to do this case. Oh boy, come on, don't kill my computer again.
6784.
What?
Oh, so sometimes when it pauses like that, I'll see what if there's a particular case and
Yeah,
it's
right.
6784.
But I think it thinks it's, I mean, maybe it already thinks it's finished, but it's just freezing. Yeah, I think it's trying to send the data back.
Oh, I see.
Come on. So, I mean, this may give us, what we're looking for is indications of universality, basically.
Right.
And, I think that the test for universality is, I mean, I don't know whether this total thing is right because well, we'll find out in a moment. I mean, if none of these, I can't believe that none of these will look non-trivial. I mean, I suppose it's possible there's no 2-2 Turing machine that does this, but I find that really hard to believe. Actually, what's also an interesting thing to look at is in some of these other pictures, we have tagged them when the thing has halted.
Mm-hmm.
And like in the multi-way graph, we've tagged it when it's halted. Okay, here comes. Okay, hopefully this is going to come in a moment.
$32,000 items.
Yeah.
This is where the good groupings help.
What did we do? We did do a grouping here. Yeah, we did do some grouping here.
Right. I just go to a stronger one.
Come on. We should be able to render this case. But okay, so let's imagine, well, we just don't know what we're going to see here. And we could also just pick random cases from this.
Mm-hmm.
If this doesn't work, we'll do that. Oh, grell. Okay, well, let's review what we had. Oh, we can't even scroll. So what do we know? We know, okay, we got this way of looking at, okay, for the case of one color on the tape, we have another kind of indicator and we can kind of see that nothing too exciting happens.
Right. Nothing but weaving of various sorts.
Right. Okay, so this case, so the first question was, could we get anything non-trivial with with one? So let's just think about that abstractly. The one state. So what can we encode with one state? So we can get, I mean, I don't see why that is obviously trivial with one state. Because it can write, it writes data onto the tape. Okay, is the deterministic case trivial with we should just write the code to look at the deterministic case.
No, because with enough not states, rule parts, you could basically emulate a random walk on a 2x2 grid.
Why?
Because basically with the multi-way part, say you could move in all 4 directions.
But we're on a tape.
Yes, but basically it's the.
I mean, no, what we're asking is, look, the first question is, can a deterministic one state thing do anything interesting?
Right.
Deterministic one state, we should determine, we should just work that out. Oh God, what is this doing? I think we're not going to be able to get this back.
Looks like it's almost done.
Can you tell?
Oh, because the bar is almost finished.
That's absolutely irrelevant.
Okay.
It lies all the time with that. But while we're doing this, let's write the essentially the mobile automaton case.
Okay.
I'll just use a different kernel here, or a different whole system here. Okay, so let's store that as okay. So now what we want is we want to say we've got a rule. How are we going to specify the rule? The rule just says, let's imagine that the rule goes -1 or +1. Let's see. Oh, for goodness sake. I can't even open that. This is really fairly dismal. Okay, that's a second copy of this. Okay. Let's say TM rule cases. S is 1, K is 2, for example. Okay, so those are all the cases. So to make a deterministic one of these, how do we make a deterministic rule of this kind? We just say, for each of those cases, all we have to say is whether it's going, we have two things. We have the color and whether it's left or right. Correct?
Uh-huh.
Okay, so let's look at my mobile automaton section here, where I had all of those cases. Okay, so the representation that we were going to use here is probably to be consistent, I want to say position, comma, tape, right? To be consistent with the Turing machines.
Uh-huh.
Now, actually, I probably should have position and then the offset, but let's just do this for now. Okay?
Okay.
So then we want to say, at each step, we're going to have, okay, so we're going to have tuples of it's one state. So the only thing we can specify in a deterministic one is for each state, whether it goes left or right. For each state, what color and left or right. Okay, so then that means that the actual thing, we can just number it by states. So we're just indexing into something. So it's just 1, -1 or something, 0, 1, whatever, for two states. So in other words, our TM rule cases are MA rule cases. Actually, MA rules for a given S will be table help me out here. For each one of these, it can be, oh no, it's a tuples, I think. Is that right? For each one of these can be any of, do you understand what I'm saying?
Mm-hmm.
So it can be any, actually I don't mean that, I mean K. And then what can be written on the tape. So it's a table of I, comma, 1. I goes to 0, K minus 1. Join that. Ugh. Minus 1. Do you agree? And then I want to tuple that up for K.
Right.
Okay, I think those are the rules for K equals 2, of which there are a total of 16.
Makes sense.
Okay, so now it's kind of annoying that there is a mobile automaton function in the function repository. I wonder how it works.
You should ask the author. No, that's cool.
Magnificent. Okay. So let's say MA step of rule, comma, and then the configuration will be, let's say we're going to say position, comma, tape. Okay, so then what we say is just it's rule sub tape of position no tape of position comma what's the second thing? Nothing. It's just tape of position and then okay, I see. It's tape of position and then for each of these values, right? Yeah, it's just 1 plus that. It's rule of 1 plus that. And then those things, it's with u equals this. And then we say replace part. Okay, it's pos plus u sub 2, comma, replace part u, comma, pos arrow u sub 1. Do you agree?
Mm-hmm.
Okay. MA evolve list, rule, Okay, so now we have MA evolve list of a rule. Let's pick a random rule here. And then the initial condition that we want would be our standard initial condition of position would be t plus 1, and then we'd have a table 0 to t plus 1. Then we'd say comma t, and we'd say with t equals 4, for example.
Right.
Wait a second. What is this doing? This is saying, okay, so that didn't work. What the hell? It made this messed all up. Okay, so hold on. Replace part. Oh, piffle. That's totally wrong. Of tape. There we go. Okay, so now well, let's just for now, let's just look at their oh God, what did we just do here? Oh. Major problem here. The array plot wants to be loss / add that.
Ah, yes.
And the interactive list selector why didn't it pick up that arrow ampersand? Arrow hash. Why is that being given literally?
I don't know.
Oh. Major problem. I don't know how it could possibly have worked.
Oh, it's just skipping parallelism.
No, it wasn't. It didn't have a map.
Oh, okay.
I don't understand what it did. I mean, it was just, okay, there we go. All right. So that's the case of size 2. So let's just try size 3.
That was fast.
I think these all have to be trivial. This is 3 colors, so why? I don't understand why this didn't give. Do you understand what I'm saying? I didn't understand why this didn't give 0, 1. See, why doesn't it give 2 and -1 there?
Good question.
Why doesn't it give different values? Why does it only give because the array plot should, and I suppose we can just, to make sure of that, we can just divide by 3, 2. I don't understand this. Do you?
Mm-mm.
Why are those values only? I don't understand. Let's pick some random ones here. Let's pick a random one here, random one here, random one here. And let's now do this without the array plot. Oh, it's only got either. That's really weird. Well, let's do the. Okay, so each one of these, let's do min-max. Well, actually, let's do counts of flatten of hash onto every one of these.
Okay.
And then let's say length of each of those. Oh, wow. There are no cases where you can get. Is that obvious? Well, let's see what happens if we don't use the simple initial condition there, if we use a slightly more complicated initial condition.
Okay.
So here we go that, and so we say replace part of t arrow 1. Hardly profound changes, but at least it did something.
Right, right.
Okay, well, at least there we've got some variegated varieties of stripes.
Mm-hmm.
Oh.
Yeah,
Hello.
some that are complicated.
Hello. I don't think they're very complicated, but they're at least not completely trivial. Yeah. Nothing very interesting. They quickly become periodic.
Mm-hmm.
Though it's a little less obvious to me if they had a periodic initial condition, what they would do.
Mm-hmm. All right.
But okay, so what did we learn from this? We learned that the deterministic case is trivial.
Yes.
I think we have to kill this over here. Try again.
I agree. You gave it an honest try.
Okay. Okay, so this, hold on. So this is what we learn. Okay, so what we learned here the deterministic case is not going to do anything interesting. So then the question is, can something happen in the non-deterministic case? How to think about this? If nothing interesting happens, I see it could happen. I mean, there's clearly a path that does this, right?
Right, right.
But there might also be other paths that do something completely different. Okay. Just evaluate all these again. Okay. I just want to make a note here. Actually, that's probably more relevant when I discuss the. Okay. Oh, come on.
Okay. I just watched everything change.
Okay, this has to come back up. Hold on. I need another piece of food. I'll be right back.
Okay.
Let's try this case then. So what we're going to do, let's get a random sample. Well, yeah, let me just get, I don't know how big that is. Oh, it was super small. Well, then let me not even bother with that. Let me just do a random sample of 100 of these.
That sounds like a good idea.
These arrows is just really weird. All right, so you know, let's do this, and let's maybe make a multi-way graph at the same time. Well, I mean, actually, this is the multi-way graph, but we could show the okay. So I'm going to do, I'm going to put the graph in there.
There's some non-trivial thing. Try for more steps, since we're only doing a sample of 100.
Well, but remember, this is a multi-way graph.
I see. The fourth from the last looks more random.
Which one? This one here?
Yeah.
I don't think so. We have to be a little bit careful going to more steps. If we see this one here, for example, has a somewhat complicated multi-way graph, but that one as well. But its kind of value indicator is trivial.
Right.
Possibly suggesting that total is not enough. Okay. Let's look at
the director of The World Is Not Enough died yesterday.
What's that?
The James Bond movie, The World Is Not Enough. The director of that movie died yesterday.
Oh, well.
Who also did the Up series.
The which?
The Up series.
Up series? What's that?
He did a documentary called 7 Up of some 7-year-old boys, and then
oh yeah, okay, that's a famous, yeah. Wow, I didn't know that was the same person. Okay.
And he wanted to retire at 84 up when he was 99, but he just died at age 70 something.
Okay, so
interesting.
Well, let's look at these with if I do this, See, that looks a bit non-trivial. But yet here, so the question is, okay, so let's take this, our indicator here, and apply this indicator to some of the other cases we've looked at. Okay. Let's look at s equals 1, k equals 2 again. And then here, okay, s equals 1, k equals 2. Okay, let's do the trivial case first. Okay, nothing very remarkable here. Agreed?
Right, yes.
Okay. So there's some things like this. Okay, this is what we did before, right?
Yes, I think so.
So in this way of looking at it, okay, so we just need to better, we need to figure out whether these things okay, with respect to total, nothing too interesting is happening.
I agree. Some of them definitely more complicated than others, though.
Right. Okay, so now let's do the same thing. Let's just take the log. Let's do the exact same thing. But instead of total,
We do the thing that caused the crash last time.
let's do log base 2 of, we got that weird comma 2 there. Okay. Log base 2 of 1 plus from digits of that thing, comma 2.
Right.
Okay, let's put it
And
in.
let's save first. Oh, it worked this time. Oh, that's pretty cool.
Okay, so like that one doesn't seem so trivial anymore.
Yes.
Now, what's the signature of total in, I mean, I just think total is actually not that relevant.
Oh, these are cool looking.
Okay, let's just go back and do the 2 case here. Just to check that case.
Mm-hmm.
Well, what about that guy? Let's just check that for a little bit longer.
Mm-hmm.
Now, I also have this way of indicating which ones are terminating, and we should do that for all of these. I'll put that in. Okay, so here, for like 10 steps. What the hell is that doing? It's a little weird.
It's converging.
Yeah, okay, let me add in this thing that does this TM applies Q thing.
Okay.
TM applies graph. This will put highlights on things. Let me just see whether I can just do this. Let me do it a slightly different way. Okay, hold on. TM applies, and then we say indicator, graph indicator. Rule T. Okay, let's try this now. Ah, wait a second. Okay, hold on, why didn't that work? That should, so the red blobs indicate that it halted in that case.
Right.
Oh, we need to decide whether we're gathering this gather by. See that gather by there?
Yes.
So I think we don't. We just need to say gather. We're not doing gather by because we want both of them to be checked, I think. Maybe. Maybe we don't. Maybe we just. Okay, this just wants to be this. There we go. Okay, let's try this again. So we want this case for this. Let's just go for 5. Okay, 1, 2, 2. Okay. Now that one is our only non-trivial one, right?
Yes.
But that one basically turns into this.
I do like the last one, though. It sort of looks like it might be a counting function. Because it seems to hit all possible values.
Yes, I think it does because yeah, right. Right. We can probably see why that happens, but we'll get the rules here. All right, let's just look at the rules for that guy. Oh, for goodness sake. Oh, I got this wrong. Okay, hold on. The indicator, the selector function, is not that, it's sub 2. Oh, for goodness sake. Maybe this should be 1, 1. What happened here? Help me out here. What's going on here?
I'm not sure.
Okay, let's look at this. Okay, so this is going to return, TM graph indicator is going to return a list arrow, a single value. Okay. So this gather by is respect to the first element. So this is, I see, that's the 1, 1 element of the gather by. Goes to the 1, 2 elements of the gather by. Brilliant.
Ah, I see.
Okay.
And you were looking at the rule for the last one.
It does just count. Look, because it always goes to the right.
Mm-hmm.
And
So from experience, you'll get the most chaos by adding one more rule to that one.
we can try that, but I'm not necessarily believing you. Okay, so let's take this. And then this whole thing here goes away. And we replace it with the 3 case here.
Okay.
It's kind of funky. Okay, let's pick out the ones we think are non-trivial. That one, that one. This one. This one. This one to some extent. Oh, I made one more mistake. Try this again. Okay. All right. Let's pick these out again. This one. This one. This one. This one.
I like the power lines one at the end.
This one here.
Yeah.
That one is unfortunately a bit bigger, so we may have trouble. Look at these guys. Well, let's add those two. Okay. Which one is power lines? It's the one 3 from the end, because that one will not be able to get as big. See what I'm saying?
Okay.
Wait a minute. Oh, there. 1, 2, 3 from the end. Delete that and put it in here. Did we leave a double comma? Yes. Okay, so now let's do this thing again. This.
The power lines is one off from a counter. The third one is definitely complicated.
This guy here.
Yes. I'm still not quite sure what's going on with that one.
What about this guy? Hard to tell, I think.
Yes.
Okay, so these are the 3 case. Did we manage to do the 4 case, or did the 4 case blow up? Was the 4 case the one that oh, this was, no, we could do the 4 case here, because this is just, so the main point is, this is not showing triviality in the case of a single state. Right?
Right.
So one thing we could do in these is we can ask the question, which values are generated here? Like in one of these, does it generate all possible tapes or not?
The counter does. We know that.
Yeah, right. But most of these don't. So then the question is, how can we characterize what tapes they do generate? So we need to get the bucket of tapes. Okay, first of all, I want to just record some of these things. Hold on one second. Okay, so this was a case that we looked at. This was a non-trivial case. The first case there. This was a non-trivial case. And those are our summaries of those. So this is all S equals 1.
Right.
K equals 2. So now our next question is, if we go to S equals 2, well, first of all, we could look at the case of 4. Let's look at the case of 4 for this. 1, 2 with a 4. And then, okay, then the remaining thing to do is to look at what the set of things produced by this is. But let's now look at this with the case of 4. How many of these are there? Are there some huge number?
It was 32,000, wasn't it? I think we wanted to sample them.
No, that's with the 2-2 case.
I see.
Boy. There's some fairly complicated stuff here. All right. Let's sample. Okay, so we had up above. Okay, let's sample the 3-3 case for 2-2. 3 case, sorry, the 3 case. What the hell is that? Wait a minute, I gave the wrong thing here anyway. Okay, so this is the sample of the 2-2 case with a 3. 2-2, let's try this case here. Now remember, we can go up to like 32 here, so. But we should pick, is there a random subsets function?
Random sample.
Oh yeah.
And then the size of the sample.
Yeah, that would do it. Okay, so let's look here at what happens if we say, okay, so some of these are a little bit non-trivial, but we don't really know how. So instead of that, we just do this, TM rule cases, random sample, comma, okay, if it's not, well, we'll not worry about the testing for determinism. They won't, very few of them will be deterministic. Okay, let's try this. Oops. Oh, come on. Random sample there. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Oh, I see what we need to do. Table of 100 of those. Oh, fiffle fuffle. Okay, so now if I take a random sample of those, why isn't that the same as what I did up here? I've got subsets.
Do you need to
Oh, I have to
do
list slash at.
extraction?
No, I've got to do list slash at that. Okay, so that's random subsets of 4. Let's just do like 50 of them with a random subset of like 6.
Some more complicated than others.
Yeah.
But pretty trivial at first glance.
Well, certainly not obviously more complicated than the other things we've seen.
Right.
Let's just see what happens if we go up to dramatically larger. Let's go to like 15. Nah. Let's not go that ambitious. Let's go 12. So some of these could get very big, right? But they could be very treed out.
Right.
Mm-hmm.
Tendency to get counters.
Yeah. Okay, but so these are so the real question is, okay, so the final thing I want to look at for right now, probably before I start to write what we already dealt with here, is the summary it's a pity that there's no time evolution visible in these things, although I suppose to some extent the distance gone is a proxy for that.
Right.
Oh, and by the way, for the s equals 2 case, we should really color these.
Mm-hmm. This is a case worth pointing out that it's a very simple case, but it generates all possible tapes with just
Yeah, I
what is that?
understand. Right. I know. We'll get to that. Okay, so I might make a note of that actually. Well, that's in the category of what do they generate, right?
Yes.
Okay. So what we need to do, given one of these things, okay, what we want okay, is TM tapes. And do we want the ones exactly at step T? No, probably. See, the problem is the ones not at step T will have to be trimmed. Their ends will have to be trimmed. That's all right. That's okay. We can do that trimming. Okay. Okay, so then that is actually what we want to do is we want to say last of to expression. And then we want to say map indexed. Okay, so we want to trim from the beginning. Doesn't pad left if you give it a negative value, doesn't it trim?
I don't remember. I don't think I've tried that. Oh, try it.
Truncates the last elements. Pad left truncates the last n elements.
Try it on range 5 and make sure.
The heck does that do? I'm totally confused by what that's doing. Let's just do a drop or a take, actually. What we want to do is to do a take of its T minus the index. Is that correct?
T minus the index.
Take
Yeah, I think so.
#1 first of #2 that's the index. So we want to go from T minus, wait a minute, at the beginning, how many do we get rid of? Okay, and then we want to go up to minus T minus first of #2. Is that right? Okay, I don't know if this is correct. Let's give this a try. Okay.
You can test one on one of the counters.
Is that a counter?
No, it's the one where everything appears once.
This one
The
here.
last one. Yeah. And you've got it already there.
Wait a minute. There's probably a +1 here.
Or maybe you need a flattened.
No, no, I don't. Okay, let's have a think here. Okay, so the first element, honestly, that should be just a single zero there. So this will be of length 2t plus 1. No, I'm sorry. The whole thing is going to be of length 2t plus 1, otherwise known as 2 times 4 plus 1, length 9. Okay? But the first element, we want to remove everything but the single zero in the middle. So we want to remove 4 on each side, correct?
Yes.
Okay, so to do that, we want to remove 4, so let's say we have range of 9. We want to say take that, comma. We want to say 4 plus 1 to minus 4 minus 1. Is that right? Or am I completely wrong? No, minus 4 plus 1. That's the first element, is that.
Okay.
Then the second element wants to be, okay, so that's t. So then I want to go down by 1. T minus that. Okay, so this is t minus, okay, so it's t minus the index minus 1 plus 1, right?
Makes sense.
So it's 2 minus the index plus t. Okay. 2 minus the index plus t minus, okay, dandy. Okay, so this is now supposedly our counter. So let's find out how many tapes there are for each one of these. Okay, so this is TM tapes there. I'm not feeling a lot of counterism here.
What did we do for?
Oh, look at that.
Oh yeah, it is a counter.
But it's not a full counter. It's a counter only on one side. See what I'm saying? Which is not surprising. It's just it's tooling off to one side.
Right.
Okay.
And the way we set up the way we set up this viewer, it winds up combining them nicely.
Well, we might want to sort these things, but let's take some other examples here, like these guys here. Okay, and let's see what their corresponding whatchamajigs are.
Right.
Should we do an array plot on each of them? Or we might.
Yes, I think so. Do we have a 3D array plot now?
We do. I think the order is pretty arbitrary. See what I'm saying?
Yeah, I'd agree.
So, I mean, I think the correct thing to do here is to say sort. Well, some are simple and some are not. I mean, there's a certain argument that this thing, oh, I see. So if we were to also plot, if we were to position this in a 3D array plot, wait a minute. No, for each of these, there's also a head position that we could give. So we could actually sort all the configurations, head position and, you get what I'm saying?
Mm-hmm.
So the thing we want to do then is if we did TM tapes and then we just made a different value here for the array plots, then we could have that be a red cell or something there.
Sounds good to me.
Okay, but then what are we going to learn from this? Because these are, let's see, these are, God, this is so weird. I mean, these don't look like any kind of simple language. They don't, there doesn't seem to be any obvious regularity to what's actually showing up here. Let's actually run these a bit longer. And some are more obvious than others, but I don't think these are super obvious. Does that seem super obvious to you? I do not understand these creatures. So, okay, well, let's put in the thing to get this. Okay, so then, okay, so instead of last of two expression, we say, okay, hold on. What do we do here? We say last of two expression. It's the last, but then we want to replace part. It's the last of that applied to two expression, but we also want to take replace part, actually map at, and then we want to say, how do we want to indicate this? We want to say -1 minus the thing, I think. So that 0 turns into -1 and 1 turns into -2. Does that make sense?
Yes.
Or we could say 10 plus it or something. Let's do this anyway. Okay. So then this wants to be that, map at that, and the position we want to map it at is at hash sub 1, 3. I claim. So that's the map at. Wait a minute. The map at should close there. Didn't work. Okay. Let's look at the map at. The map at is that Okay, that's the map at.
There's a comma after that?
No, that thing, that map at is applied to
I see.
this expression. Ah, that bracket is wrong. Okay. So now, if we do this up here, and then we really want to color rules there. Okay, so color rules goes to 0 goes to white, 1 goes to black, -1 goes to, let's say, yellow.
Instead of white, I'd use light gray.
Well, I like color. Let's go -red, -2 arrow dark red. Oh, we didn't check that TM tapes heads works correctly. And it doesn't. Oh, piffle. What's that doing? That has to do with our... Why is that? Why does that make any difference? Map at. Do you see my points here? This is the map onto this.
Right.
And then the map indexed. Well, let's echo this here so we see what it gets before it gets the map index. It's already toast at that point. Oh. The map at. Is that the head position? Why is that? That's not wrong. That's the head position, isn't it? 1, 3.
I think so.
Oh, no. It's 1, 2. Yeah, the third one is the offset. Okay, so this is showing. Let's go to 8 here. And we might as well just drop the first few. Okay, let's look at this. That is not a simple puppy.
Oh, definitely not.
I mean, it's somewhat simple, but it's not, I don't think it's particularly simple. And I wonder if we gave it a different initial condition, whether it would produce very different stuff.
I imagine you're right.
giving it a different initial condition. Oh, we don't have a good way to do that. Well, we could probably do that. All right, look, I think I should write about what we know so far. Let's look at with this way of doing it. Let me just get rid of these because I don't really care about these. This is okay. Let's look at our counter.
Right.
Something went horribly wrong there. There we go. Counter, counter, counter. Okay, so there should also be ones that make like Fibonacci words and so on.
Yes.
And I mean, let's do this calculation for, let's maybe add this in. To these, just to see what they do. So we're going to do all three of these things.
Okay.
I'm actually going to do this. I'm going to say sort last of a 5. Okay. I'm going to put that. All right, let's try that. Oh, you know what else we want to do? We want to say, where is it? Array plot. And let's add an option to the array plot that says aspect ratio goes to 1. Okay, so there's our counter. There's another counter. And we have yet another way to understand these by looking at kind of the branching. Okay, so some of those have slightly more elaborate, although that doesn't look terribly complicated. Do you agree?
Right, yeah.
Let's just go one more couple more steps here. That's a little weird.
Mm-hmm.
Well, let's just look at that one. This is a little weird. Okay. And I don't understand why this would be so similar to this, yet not quite the same.
Right, right.
Let me just make a thing that does this. Okay, I don't really understand that. Let's go like 11 steps. What the hell is that doing? Do you understand that?
Not really, no. Looks pretty though.
Great. Let's look at this. So this is 1, 0 goes to 1, 1 minus 1. Okay.
I'm thinking it's a counter variant.
Yeah, well, should we look at what it does? I mean, it's kind of weird. That's not a very complicated thing.
Right.
Let me just try something else here. Oh. That's what it's doing in multispace.
Ah, okay.
But that's only showing the let's see whether we can get a picture. Hold on 1 second here. Oh, for God's freaking sake. I have to rerun this with animation stopped. Thank goodness for that. No, what the hell is this stupid thing? You know, this is really dumb. I don't freaking believe it. Okay, so hold on a second. Okay, this will be more civilized. This is really stupid that this just animates by default.
Right, right.
Yeah, it's a separate question. Why are there nodes that seem to come from nowhere there? Oh, for God's freaking sake.
Uh-uh.
Okay. So we were just looking at this guy here.
Right.
I don't think I necessarily care about animating that guy. I mean, oh yeah, I know what I was looking at. I was looking at, before I did that at all, I was looking at this thing here. Ah, ah. Oh, this is so freaking stupid. This is so annoying, this bug. Okay, so can you see what it's doing here? Maybe if I make it a lot bigger, we'll be able to see it.
Right. That sort of fits with what we're seeing in the new fancy graphic we made.
Well, but what are we seeing? Explain what the set of states that this generates is.
So something occurred to me is we could, instead of a plain binary number, we could make this as a binary decimal with the head position indicating where the decimal point is.
Yes, we could. That's not a bad idea. Hold on, let's think about that for a second.
And then the zeros won't matter.
Okay. That's an interesting idea, but what is this puppy doing? What is this doing? I mean, but the numbers could get quite big. Well, I guess if we divide, well, right now we're taking a log, right?
Right. It doesn't look like there's every group of ones is contiguous, it seems.
Well, that's what we see here.
Mm-hmm. And the head position is always in the first few of the one positions.
Yeah.
That does map in well with the graphic we've got that up there. Interesting.
Yeah. think this may be the same one we're looking at. 1, 0 goes to 1, 1, minus 1. No, it isn't quite the same. Oh, this is the same. No, it isn't. Yes, it is. So in a sense, we're having collections of those kinds of things. And then, okay, so then I have this notion of multispace, of plotting and then in a sense, we've got yet more visualization that we're doing here.
Right.
Let's see. Is the binary decimal thing? Yeah, it might help. I mean, it might help. It might help. It might help. I'm getting tired, actually.
That might explain the irregularity in the last row, too.
What do you mean?
I'm not sure. I'll need to think of it more.
Okay. Well, maybe you can you should have access to all this code, I hope.
Yes. I got a Dropbox link earlier today.
Okay. Well, okay, we can, let's see, in here, instead of using this, we'll use something where because this does take account of head position because that's the X coordinate.
Mm-hmm.
So, all right, so what you're proposing is that 19. Oh, I see. There's that from digits there. Okay, so instead of the from digits, we want to say real digits, if I'm not mistaken.
Mm-hmm.
And then we want to say, so let's see how that works. So actually, we want to just say from digits, not of the thing, but of that listed thing, right? What does real digits return? So if I say real digits of 12.3456, okay, so it says comma 2. So we want the head position. Gosh, how do we do that? We want it at the first, we want it at the units column or at the first decimal column?
I think you can do either.
Okay, so I think that if we say from digits of that, we get that.
Oh, okay.
I think it's as simple as just adding to the from digits.
The head position.
Yeah. which is actually 1, 2, right? So it's this, it's this, kind of inefficient that we keep on doing the 2 expression, but I think it's just that.
And we won't need the log 2 anymore.
Yes, we will.
Well, the tape doesn't grow nearly as fast now.
I think we'll still need the log 2. It still can get big. It's still
Okay.
going off to the left. I mean,
That's true. That's true.
Okay.
Let's try it with just the counter to see how that changes things.
Well, to be perfectly honest, I've got the whole setup is so complicated, I might as well just do it here.
That's true. Kind of interesting.
It's kind of interesting. I don't know whether it's really helpful. I mean, I'm not sure it doesn't lose information. I mean, it's because the other one, I'm not sure whether this is useful. God, these are complicated looking.
Mm-hmm. Well, it's another visualization we've got access to.
Right. All right, let's make a plan. So some of these ones like that, the pseudo counter, it'd be really nice to unravel a pseudo counter.
Okay.
I think it'd be interesting to think through. Okay,
And
so here's a question.
that's already on the list of needed items is number 8. I'll just make a note that we're going to call that pseudo counter.
Wait a minute. How did it get on the list of needed items?
There's an irregularity in the last row of it that you wanted to figure out.
Okay, fine. All right. Okay, so let me ask you this question. Could we prove that the case that let's just have a little think for a second about proving that the what am I saying? That the case the one state case, can we emulate a two state thing with a one state thing? That's the question.
Interesting question.
Because if we can do that, then we can prove that one state is enough.
Okay.
So how would we do that? So what we would do is the thing would probably go kind of, it's how would it do it? It would use another one of its rules somehow. How would it do it? So it's got, by the way, there's a whole other can of worms to do with multi-headed. I wonder what on earth would happen with all this stuff with multi-headed Turing machines.
Oh, I realize the answer for the irregularity is it's a product of weaving.
Okay. Well, but can we think for a second about the simulation thing?
Mm-hmm.
So what we want to do is emulate the multi-way system of another rule with one rule, okay? So in other words, can we get, if we ignore, okay, let's ask the question, can we emulate the tape states, even if we, or the position, but not the state of the head, right? If we ignore the state of the head, can we emulate a two-state thing? Well, actually, no, let's say we want to encode the state of the head. Can we do that by having, for example, a head with a neighboring cell? See what I'm saying?
Mm-hmm. I don't know.
Well, how about think about that? I mean, could we do that? And then the thing would be, okay, so the question again is, can you reproduce the multi-way system up to some compression or something, up to some two steps is one or something like that? In other words, one way to do that would be, let's take a 2-2 Turing machine and let's see if we can reproduce what it does. Okay, so what we have is it's in an up state and it has a rule that says apply only in the up state. Okay. But then, so in other words, there's a branch that can start if it's in the up state, but doesn't start if it's in the down state, if that makes sense. A branch of the multi-way system, because there isn't a rule. If it's in the up state, it transforms. If it's in the down state, it doesn't transform, let's say. Okay?
Okay.
So the question then is, boy, I bet that this can be done. I bet you can show that for any set of those rules, all right, why don't you think about this? I think this is the type of problem you potentially could solve, right? So the question is, right, the emulation of, okay, we just got to think about what does that multi-way system mean? The 2-2 multi-way system can be labeled, its edges can be labeled by, I'm fairly confused. Although it just does seem likely that you can do it by just including more one state transformations. I have to say that one would think somebody would have worked this out.
Right, right.
But I did look, and I remember there's a thing from 1956 about this stuff, and I did look at that. I mean, I have it in a book form, and they didn't really say anything there. Um, Great. Every non-deterministic Turing machine has an equivalent deterministic Turing machine with an exponentially larger number of states.
Mm-hmm. Okay.
Actually, the simulated in exponential time is actually the more important point. Because it's trivial. It's trivial. It's obvious how you can do that. You're just evaluating. You're just computing the multi-way system.
Right.
Oh, great! Everybody proves the same theorem. Brilliant.
Well, it is after 1 a.m. over there.
Yeah, I'm just looking to if I can find anything here. It would be amazing if nobody had looked at this in all these years. Because Shannon, for example, looked at well, on page 2 is already what this kid from the summer camp did, summer school did.
Right.
Which is not encouraging. By the way, I should make sure to mention this in here. Let me just ask Nana this question. Let me just look up one thing that I think might be relevant. Oh boy, that's amusing. Guess where this is? Look at that. The top hit on the web to Shannon's paper is on our website.
Okay.
Okay. Turing machine with 2 internal states. I mean, this is a trivial paper. It's just saying that you can get the impossibility of a one-state universal Turing machine. Okay. An interesting unsolved problem. Well, we solved that one. The answer is 6.
Okay.
That was what our Turing machine prize was about. Okay, but this is all deterministic machines. So again, the question is, can one make a machine? Okay, so I think the right way to do this, as I say, is to take a machine which is a 2-2 machine, right? And to ask the question, can you get the same multi-way graph from a 2-1 machine, for example, or even a 3-1 machine or whatever?
Okay.
Okay. So that's what I would try to do. And a quick answer would be much appreciated. All right. I think we should wrap here. Thank you for your help.
Oh, you're very welcome.
And until the next hunt it's just crazy. It's just crazy. One would have thought by now that all of this stuff would have been mined, but it absolutely has not. I mean, I can't believe that something as elementary as this hasn't been mined. It's only been, well, let's see, when we're non-deterministic generation. I think Alan Turing's original paper had these in it.
Yeah, but you kind of need a computer to really look at these well.
Well, yes.
So it's only been the last 10 or so years that this was a conceivable search, and you're the first one.
No, that's not true at all. I mean, well, okay, I admit, if you've actually got to use graphs and graph visualization, yes, I agree. Yeah. Okay, it's looking at you here. Okay. See you later.
All right. See ya.
Bye.
Bye.
Bye.